Okay, time is almost up and let's start. Good afternoon, everyone. Welcome to be here. It's my pleasure to have this opportunity to share the testing of large-scale edge computing using KubeEdge, as well as the work we have done to ensure the stability at a scale. Before starting the presentation, let me briefly introduce Yue and myself. Yue is the software quality engineer of DaoCloud, and she is also the chair of SIG testing of KubeEdge community. My name is Yue Bao, and I worked at Huawei now, and I'm currently also a maintainer of KubeEdge community. It's a pity due to the scheduling conflicts, Yue is unable to attend this conference in person, so she interested in me to share this topic. Okay, let's talk about some background. With the rapid development of 5G networks, industrial IoT, AI, and other fields, edge computing has become a trend, leading the digital transformation. Future scenarios such as smart cities, smart transportation, smart healthcare, and intelligent manufacturing become more familiar to people. And edge computing has garnered much attention. Gartner has pointed out that in 2023, the number of the smart devices at edge is more than 20 times that of traditional IT devices. And by 2028, the integration of sensors, storage, computing, and advanced AI capabilities in edge devices will grow steadily. Due to the diverse types and large numbers of IoT devices, the increase in the scale of IoT device connections brings significant challenges to unified management and operation and maintenance. At the same time, users of the KubeEdge community have also impressed demands for managing large-scale edge computing, edge nodes, and edge applications. For example, in the high-speed tool station project based on KubeEdge, nearly 100,000 edge nodes and over 500,000 edge applications are connected at highway tool stations across the country. As the project evolves, the scale of edge nodes and applications will continue to grow. The Vehicle Cloud collaborative management platform built using KubeEdge is the first cloud edge-end integrated architecture in the automotive industry, enabling rapid software upgrades and integration for software-defined vehicles. In this platform, each car is treated as an edge node, and the scale of edge nodes is expected to reach millions. Before diving into how KubeEdge achieves large-scale management and testing, let me first give a brief introduction about the KubeEdge project. The KubeEdge community is the industry's first cloud-native edge computing framework, and it is designed for edge-cloud collaboration in edge computing scenarios. It focuses on providing a consistent experience for cloud edge resource collaboration, data collaboration, device collaboration, and intelligent collaboration. So far, KubeEdge has get over 8,000 stars and 2,200 forks on GitHub, and we also have more than 1,500 contributors from more than 100 organizations worldwide. And there is also exciting news. In October last year, KubeEdge has become the CNCF graduated project. Okay, this is the architecture of KubeEdge, which covers the cloud, edge, and devices. Which means, in other words, cloud, edge, and devices are connected together seamlessly with KubeEdge architecture. In the cloud, KubeEdge is built upon the native Kubernetes. We don't make any changes to Kubernetes, so users can use the native Kubernetes APIs to manage edge resources. In the cloud, we have a cloud component which called Cloud Core, and the corresponding component at the edge is called Edge Core. Cloud Core at the cloud will list watch the cluster and get the resource, especially the edge resources, and send the message to the edge. The cloud core and the edge cores connection is using the cloud edge messaging channel defined in KubeEdge. It is a stable channel. We will introduce it later. For the edge core, we integrate a lightweight kubelet. It retains the core capabilities of Kubernetes while removing features are not used on the edge. The native Kubernetes interfaces are fully supported in the edge core, enabling the management of edge containers use CLI interface. On the right is the devices side, where we support devices based on various protocols can connect to the edge core and to communicate with the cluster. Okay, first we need to define the service level indicators and the service level objectives, which called SLIs and SLOs. Since KubeEdge is developed based on the native Kubernetes, we reused some Kubernetes-defined SLIs and SLOs, such as API call latency. The API call latency demand the SLO, such as requires 99% of latency to be less than 1 second. And for non-streaming read-only APIs, the P99 latency should be less than 1 to 30 seconds depending on the scope. Additionally, we also defined the port stand-up latency, requiring the latency for stateless ports to be less than 5 seconds. Only when our testing results meet the SLOs can we claim that our cluster meets the corresponding scalability requirement. Okay, in Kubernetes clusters, there are many resources, such as nodes, ports, namespaces, and custom CIDs. Therefore, scalability cannot simply be equal to the number of the nodes. In actual Kubernetes clusters, various dimensions are not completely independent. Stretching one dimension often compresses others. For example, if we deployed a large number of ports in a cluster, it may limit way to create the other resources. So we need to choose the testing dimension according to our specific usage scenarios. Kubernetes also recommends some scalability dimensions and thresholds. For example, Kubernetes supports a cluster with 5,000 nodes and 150,000 ports. However, the scenarios faced by KubeEdge and Kubernetes are different. Testing all dimension is challenging. So for this test, we choose classic application scenarios for KubeEdge based on meeting the SLIs and SLOs. We tested a single cluster manager 100,000 edge nodes and 1 million ports. Next, let me introduce some our testing tools. The first one is the EdgeMark. EdgeMark is similar to the KubeMark and is used for scalability testing of KubeEdge clusters. In the diagram, there are two clusters. The Kubernetes master clusters represents the actual testing cluster, and the right one cluster, EdgeMark Kubernetes master, represents the virtual cluster. When we deploy the EdgeMark ports, the port start and it will register as a virtual edge node in the EdgeMark master. So with the EdgeMark tool, we can use limited resource to simulate large-scale Kubernetes and KubeEdge cluster. So use this tool, we can expose cluster management issue only arise in large-scale scenarios. Another testing tool is the cluster node tool. It is an open source Kubernetes node testing tool. It tests the SLIs, SLOs defined by Kubernetes to verify whether the cluster meets the various service quality standards. Cluster Node 2 also provides visualized data for cluster issue diagnosis and performance optimization. It generates a Kubernetes cluster performance report with detailed results for various performance metrics. And this is the final deployment model for the test. The Kubernetes management place uses a single master deployment with etcd, KubeAPI server, kubeschedule, and kubecontroller, each deployed as a single instance. The KubeEdge management plan deployed the 5 instances of Cloud Core. The master node IP connects to the KubeAPI server, and the source board node balancer exposes service. Virtual edge nodes can randomly connect to the one of the Cloud Core instances with the node balancer. And the right is some version of our the test in the Kubernetes and the KubeEdge. Here are some specific configuration used in the testing, including the QPS and burst parameters for various components such as kubeschedule, kubecontroller manager. And since Cloud Core aggregates and processes message from edge, it has many resource handling workers configured here. So we defined some such as update pod status workers here. If you want to know more about the detailed configuration, you can refer to KubeEdge scalability testing report. Okay, this is the final test result. The chart shows the API latency metrics compared to the SLOs we introduced earlier. For example, the latency for modification APIs is less than 100 microseconds, and the read-only API latency is less than 1 second. The result meets the SLO requirements. And this is the testing result of the port stand-up latency. here the diagram you can see the latency for each stage of port stand-up and operation. The top row is the end-to-end port stand-up latency with P99 of 4,087 microseconds, and the SLO requirement of the port stand-up latency is 5,000 microseconds, so we meet the SLO's requirement. The overall test results shows that both API call latency and port stand-up latency meet the SLO's requirement defined by the Kubernetes community. So we can say Kubernetes and KubeEdge cluster can stably support 100,000 edge nodes online and manage over 1 million ports. In actual production environment, due to the network security, partition management, and other issues, edge nodes and the cloud network are not always connected with each other, and may connect on demand for maintainers. Based on the online or offline ratio of edge nodes, the scale of the edge nodes managed by a single cluster can be expanded. Additionally, by using data sharding technology to store different resources in the corresponding etcd storage, even larger scales can be achieved. In the remaining time, let me explain how KubeEdge achieves stable operation at scale. First, KubeEdge uses an efficient cloud edge message channel. As we all know, in native Kubernetes cluster, every node must network its own resources, the ports assigned to it, and all service metadata. With the increase in nodes and the ports in large-scale cluster, the number of the network requests grows very rapidly. So, significant increase the node on the KubeAPI server. KubeEdge uses a bidirectional multi-post cloud edge channel that supports WebSocket and Quick protocols. Edge core initiates connections to Cloud Core, and Cloud Core will network the change to Kubernetes resources and proactively pushes the metadata to Edge core. So through the Cloud Edge channel, this will reduce the node on the KubeAPI server and improves cluster performance. And second, KubeEdge ensures reliable and incremental cloud edge data transmission in scenarios with complex edge network topologies and no communication faces challenges like high latency, intermittent disconnections, and frequent reconnections. When the network reconnect and edge nodes reconnect to the cloud, large-scale fullness requests from the edge to node can overwhelm the KubeAPI server. KubeEdge uses an incremental data push model, and Cloud Core will record the latest metadata version successfully sent to the edge. Upon reconnection, only incremental data will send to the edge, solving the problem of fullness request and improving stability in high latency, low quality networks. Additionally, in the edge, we we complement edge core on the edge side, trims the native Kubernetes, removing unused features like entry volumes and cloud providers. It compresses status information and optimize resource usage. So edge core require only 70 megabytes of memory at minimum. This reduces the communication pressure and ensures stable operations even in high latency and high jitter environments. Currently, we have only tested large-scale nodes and ports. Moving forward, we will focus on edge devices, edge cloud messaging, and edge service meshes. For edge-specific scenarios such as large-scale network disconnections and high-latency networks, we will introduce new SLIs and SLOs to evaluate service quality and conduct further large-scale testing. Okay, that's all about my presentation today. Thank you for your attention. If you have any question, welcome to visit the KubeEdge booth at 14B and communicate with us. Thank you again.